Let's work out some numericals on electric potential due to dipoles. So here's the first one. We are given a dipole, there's a point dipole, tiny dipole, whose moment is given to be 3 times 10 to the minus 8 coulomb meter. This is not centimeter, this is coulomb meter. And we are asked to calculate what the potential is going to be at distance of 2 meters from that dipole along the axis. So how do we do this? Well, in a previous video, we already derived what the expression for the potential due to a dipole anywhere is. So let me quickly show you that. We saw that if you have a dipole, let's say there's a negative charge, there's a positive charge, separated by some distance we used to call 2a. And if you want to know what the potential at some point P at a distance r from the center of the dipole, this, then we saw that that expression is going to be k q into 2a cos theta, where theta is this angle, theta, divided by r squared. And how did we derive that? Well, we calculate what the potential here is going to be due to this charge, potential here is going to be due to this charge. We added them, and then we did some mathematics where we said, okay, let's assume that P is to be very, very far away. And if you need some clarity or you need a refresher on how did we derive that, where does it all come from, it'd be a great idea to pause this video. It'll be a great idea to go back and watch our video on the derivation of electric potential due to dipoles. But anyways, let's continue. What's given to us is we're not given q, we're not given the distance, we're given the dipole moment, and we're given some vector. What is that? Well, remember that this product itself is what we call this product of charge and the distance. That itself is what we call the dipole moment, which we represent as P. And what does that direction say? The dipole moment is taken to be a vector, and its direction is always from the negative charge to the positive charge. So this is your negative charge, this has got to be your positive charge. So in here, dipole moment is this way. Okay, and so to think about that angle, the theta is the angle between the dipole moment vector and the vector that points towards P, the r vector and the dipole moment vector. That's our angle. All right, so why don't you pause the video and see with this now, can you go ahead and solve this particular problem? All right, so let's do this. So what is k? K is that familiar 1 over 4 pi epsilon naught, whose value is 9 times 10 to the power 9. And I don't know the charge or 2a, but I know the total product, that's dipole moment, that's given to me as 3 times 10 to the power minus 8. And what is cos theta over here? What is theta? Well, theta is this angle. In our case, notice, if I were to draw that vector from here to here, that angle is 0. The two are aligned, so cos 0, so write that, cos 0 divided by r square. R is this distance, 2 meters. So 2 square is 4. And it's in meters, so I don't have to do any conversion. And therefore, all I have to do now is solve this. So I get cos 0 is 1. So this will be 27. This will be 10 divided by 4. So that's 270 by 4. That gives me 4 6 are 24, 3 carries 30, 4 7s are 28, 2.5. And there you have it, 67.5 volt. That's the potential here. We're getting a positive sign. Does that make sense that it's positive? Yeah, because the point is closer to the positive charge and a little farther away from the negative charge, so it makes sense that we're getting a positive voltage. Let's try a second one. Again, we are given a dipole. This time we have charges given, the distance between the dipole is given. We have to find the potential at point P at a distance 10 meters from the dipole. And again, notice that this is a point dipole. This distance is much smaller compared to this, so we can use the far away approximation, the same thing that we did here. So again, can you pause the video and try solving this one on your own? All right, let's do this. So we'll just substitute this value. So you get Vp is equal to k is 1 by 4 pi epsilon naught, that's 9 times 10 to the power 9. Q is the charge that's given. And remember, we just have to calculate, put in the magnitude of the charge. The sign is already baked in when we derive the formula. So just the magnitude. So 3 times 10 to the power minus 6. Minus 6 because it's a micro. Micro is 10 to the minus 6. And times 2a. Now, one of the mistakes I used to make while substituting over here is 2a, I used to put 2 times, say, 1 millimeter, but it's not. This itself is 2a. Remember, 2a is the distance between the two charges, okay? So 1 millimeter itself is my 2a. So it's 1, and a milli is 10 to the minus 3. So let's take care of our 10 powers. Times cos theta. What is cos theta? Well, there's a 60, so we might write cos 60. That's wrong. It's not cos 60. Can you pause and think a little bit about why it's not cos 60? All right, let's see. What is theta again? Remember, theta is the angle between the dipole moment vector, which starts from negative charge to the positive charge, and the r vector. So over here, what is our dipole moment vector? So dipole moment vector is from negative charge to the positive charge. It's downwards this way. This is our dipole moment vector, and our r vector is this way towards p. And so notice the angle theta is this angle, and that's not 60. The whole angle is 180, so this is 180 minus 60. So that's our theta, 180 minus 60. So let's correct that. So that gives us 180. I can just write 120, but I like to calculate this way using our what do you call it? Allied angles? Yeah, allied angles. I think that's the term. But anyways, so divided by r square. What is r? R is 10 meters, so it's gonna be 10 square. That's 100. So let's see. We just now have to plug in. So 9 times 3 is 27. Times this, and this cancels out. See, 10 to the power 9 minus 6 minus 3 minus 9. That nicely cancels out. What is cos of 180 minus 60? Well, I remember the allied angles thing. If cos of 180 minus theta is, since this is in the second quadrant, I write ASTC. So in second quadrant, cos is negative. So it's going to be minus cos 60. So this is going to be minus cos 60. And cos 60 is half. So I'll get minus half over here. Divide by 100. And that's going to be 27 by 2, which is, what is that? 18.6. No, 13.5. So it's negative 13.5 divided by 100. So that's minus 0.135 volt. And so let's think about, does it make sense that we're getting a negative sign over here? Yeah, because this time notice that point P is a little closer to the negative charge compared to the positive charge. So even if we had wrongly substituted this as cos 60 and gotten a positive value, we could just look over here and say, hey, that's supposed to be negative. And then I could have like realized why am I getting a positive value, and I could have gone back and corrected myself.